further ado, over to Chris.
Thank you. Well, welcome. Thank you very much for coming along. Yes, I was asked to give you guys a bit of an overview on Secure and the IoT, which is kind of really what Crypto Quantique is about. We're trying to help customers simplify the creating of products that can connect to a cloud service, which is pretty complicated. I don't know where everybody is with regards to security and cryptography and stuff like that. So I kind of have put some slides in about keys and things, which hopefully you'll find interesting. But if you don't, sorry about that. If you're kind of an expert in cryptography, but hopefully you'll learn something today from our industry. So a bit about me. So yeah, I'm some old guy. I started out at GC Marconi a long time ago, about 100 years ago, out of uni, doing head-up displays for fighter aircraft like the F-22, things like that. So it's pretty cool stuff. I really thought I was kind of like Star Wars, didn't I? I was there for about 15 years, and then I went to Semiconductor, which was kind of a bit of a shock from a kind of a slow company, but of course high tech, to a sort of commercial whiz bang that happened today kind of company. So it was really great experience. I thought I'd only do it for about 5 years, but I ended up there about 14 years. And then I wanted to try a bigger company, sort of a big behemoth of a semiconductor company. I went to Renesas just to try that out for 6 years there, got a bit bored, and then I started going into startups. So I joined a startup in Cambridge called Secure Thingz. Basically, trying to connect IoT devices to the cloud securely. So it's kind of where I learned a lot about security. And then I was asked to join Crypto Quantique about 4 years ago. So that's me. So what I want to cover is just tell you a little bit about CQ, a bit about legislation, which is kind of cool for us because in a few years' time, people are going to have to make products that are secure, that connect to a network, and they're going to be forced to due to European legislation. You won't be allowed to sell products in the EU to do. So that's quite cool for us. It's kind of pushing the market. So a little bit about secure by design, what's involved in making a secure connected device. Some of the functions that some of you are probably familiar with security, like cryptography, hacking, asymmetric keys, etc. Talk about a root of trust, which is very important in a microcontroller or microprocessor, which is typically used in an IoT device or an edge device. Running Linux or something, you typically need a root of trust. Took a little bit of chat about that. And then I want to talk to you about how we have some path technology or physically unclonable function and how that's used to really secure connected devices. And then a little bit about connected to the cloud, how hairy that is. And then I'll do a little bit of a demo on our products. So who are we? So we started in 2016. Our CEO is a cryptographer. He studied in London, degree in cryptography. So he's kind of cool about all the NIST standards that are coming out now. He knows all about that stuff. I'm not a cryptographer by trade, so don't ask me too difficult questions on cryptography. And then our other founder is ex-Philips IC designer. So the two got together and they developed this path technology and also our SaaS platform. So we're just based over in near Blackfriars. For me to come today. So this is what we call a FUD slide. We use this when we're pitching to customers. So FUD is fear, uncertainty, and doubt. It's to respect the customer. Just to give them some idea of how big this problem is. Connecting devices is growing. It's certainly exponential, and it will continue to grow. So these are just some of the numbers explaining how many connected devices are going to be out there and how regulation is coming. So a bit about legislation. So I won't bore you too much about this, but it is important because it's starting to come out more and more. So typically America or California was the first to actually put some legislation in place for products that connect to customers' network. They went straight for the first one. So if you look at all the different things that allows hackers to get into your network, the first one that was typical was default passwords. So that was the first one that they did in California. Basically, they banned the use of default passwords in products. So, you'd go to Comet, buy your device, and it would have a password on the side, and typically you wouldn't be able to change it. In the old days, it was just that was it. You could change it if you wanted to, but it was always there. So they banned the use of that. So you could be given a password on the box, but the first thing that happened when it powered up was you had to change it. So that was the US. It's kind of spread slowly throughout the world. Europe typically is kind of a forerunner, but a little bit slow. So they have a huge amount of legislation documents, which they came out in March, which is the CRA, Cyber Resilience Act, and that kind of comes into they let people have a lot of time to read the act, figure out what they have to do, because it is expensive if you've got like a massive network of connected devices out in the field, and all of a sudden you've got to convert them to a secure device. I mean, in case of say a remote control pump in a sewage works, there's thousands of them around. You can imagine having to go out and retrofit all those. It's very expensive. So they get time to look at it, and I think it's end of 2027 that they've got before they have to have secure products. So lots of legislation. The big one for us in Europe is the Cyber Resilience Act. So this is where it covers hardware components. So it's hardware products and components placed in the market separately, typically laptops, smart appliances, mobile phones, network equipment, or CPU. So these are the things that have to be secure. Non-commercial projects or military stuff we cover, and then areas that's already regulated. So automotive is regulated to the hilt, so it doesn't really cover them. They've got that automotive got their act together already, so that's not a big problem. So for instance, if you're making a product, so you're developing as a manufacturer that you are going to place in the market, so you are responsible for getting CRA compliance for that product. So you can use obviously other products that are out there. Here's some examples of just kind of mobile devices, but we manufacture the final product on the market that has to get the CRA compliance, which will actually only be the way he'll be allowed to put his CE mark on the product, which is kind of important. That really is going to force people to sit up and listen and get this resilience act. And the reason we pitch this to shows and things is because our products can help customers comply with this act. So it's kind of a killer act as well, actually, because this is just some of the timeline of it. Typically with the European acts, there's a lot of documentation that you need to do to comply with the act. But there's an awful lot of reporting that you have to do. And they actually are going to force you, once this starts, if you kill a product, you still have to report to it for like 5 to 10 years afterwards. It is expensive, actually. It is quite a big deal. But it's important. I mean, the key is to be able to do year updates, I guess, is one of the most important things. So you can patch vulnerabilities as you find them, because in 5-10 years, you're absolutely going to find some kind of vulnerability in your product. So it's important that you're able to update it. So that's just one of the things, but this gives you a timeline of how it's done. So that's the end of the legislation. So secure by design. So it's great telling people, right, you need to comply with all these standards. You need to understand things about over-the-air updating, secure boot, roots of trust. There's lots of complex stuff, and people need some help. So some years ago now, 4 years ago, I think it was, the UK government published this pamphlet. It wasn't too bad, actually. It wasn't too heavy, and it was called the 13 Best Practices. So it was just kind of giving you an overview of don't use default passwords, try and use secure boot, telling you a bit about how to secure your memory, how you should think about security, like what is your chip going to be doing that's on your network? Is it going to be handling sensitive data or not? Is it going to store it? All these kind of things. And then kind of just common sense things like backdoors are a classic. So people will make a product and they'll build a PCB and they'll do some commissioning on the board, and then they'll maybe make some tweaks and go to production. And the engineers will maybe leave a couple of pins on the board that allow them to access like a UART or something, just so that they could easily access the device if there's a field problem or something like that. And these are typically how people get into these products. There's a great organization called the IoTSF Security Foundation, and they do talks every year. And usually they always have some guys come up who are like white hackers, who come up and tell you about the latest silly vulnerabilities that have been found on products. And some of them are just hilarious. They're really worth looking into. My favorite was a fingerprint padlock. So you could buy this padlock and it had a sensor on it, and you put your fingerprint on it and that would lock it. So they kind of got this in, and somebody said, oh, see if you can crack that. It's like totally secure. And so I had to look at it a bit. Not too bad. And they sort of looking it's as simple as that. They were just looking at the metal. That's some weird looking metal. So they just got a blowtorch on it and just melted the whole casing away. It's, silly things like that, very easy to crack. So that was quite a good pamphlet. That fed into the European standards, which is, so that was 13 best practices. This turned into 150, classic EU. But it's really good, actually. Can't take away from this. A lot of work done into it. And it tells you about, the best ways to ensure that your product is secure and moves on from the best practices. And then the ITSF, they're the good guys. Go and have a read of their stuff if you're interested in securing a product. They do this best practices guide, which talks about it in a little bit more detail than best practices over there. So just some documentation to kind of how do you actually secure a device. So there are different areas of security that they cover. The data that you're using, as I mentioned, physical security, can you actually get to the device? Sometimes you can put a mesh over it. And if somebody breaks the mesh, then you kill the device, or actually put it in a tin can or something, seal it in. There's all sorts of things like that. But the ones I really want to raise is, we'll talk about a bit more, secure boot, which is really, really important and quite complex to do. Secure software updating is really, really important. And then encryption, of course. So, security functions. So, has any of you had any experience with, because you're all IT kind of guys? Yeah, so it's mainly sort of Linux systems, is it? PCs you deal with, if you've not really sort of dealt with smaller microcontrollers and things like that? Yeah. Okay, so there's obviously a lot of semiconductor vendors out there, and over the last 10 years, they've certainly taken up the mantle of trying to make secure devices. It's been difficult for them because they've had to add these peripherals. I mean, they've had like an AES encryption decryption hardware for a long time now. In quite old parts, you can get that. But adding things like secure boot mechanisms, bootloader update mechanisms, which is difficult to do. Programming, encrypted programming, that kind of thing on bare metal. They sort of add these things as the years have gone by, but they've still found that people still want it for free. People are not willing to still pay for this hardware. It's been a struggle for them, but they've continued, and some of those devices that are out today are pretty good, actually. As it says here, the implementation is very complicated. Quite a nightmare for the embedded firmware engineer who has to deal with these peripherals and make sure they work correctly. You do have to have a lot of expertise in embedded firmware engineering. You have to know, what hardware you're talking to. You have to deal with bootloader, head configurations, and swapping bootloaders, updating your over-the-air code, and then having to deal with complex stacks such as TLS stacks. So it is complicated. So these are some of the examples of the guys that I would say are the top guys. Microchip, you've probably all heard from them. They do sort of these authenticator chips, which are pretty good. They're basically a secure element. So they're a hardened chip, but inside they have like random number generators, and they can generate keys and sign things like that. Infineon do their edge lock secure elements. Scilabs are pretty advanced. They do a thing called a secure vault, which is like a secure element inside the microcontroller. It's pretty good actually, that one. But I would say ST are probably the leaders, and they've recently brought out an STMH5, which uses their secure manager block, which allows you to actually put secure code inside this separated peripheral, which is behind a firewall. It's all, you can see, CSIP certified and PSA certified. It's quite advanced, and I would say they're probably the most advanced today. But again, trying to implement secure boot and all these other cool features, can be quite complicated. The software can be quite complicated. So I do need to talk a little bit about cryptography. Anybody use cryptographic keys or crypto guy? Okay, let me talk to you a little bit about keys then. So cryptography, so it's the science of exchanging information in plain sight under the presence of a malicious. So this is where you want to transmit data over a wire or a radio, and you want to make sure that nobody can see your actual data that's in there. And we do that by using cryptography. So the main goal is to either read communications or disrupt messages. So they want to actually see what's actually going on, or they want to capture the data, change it, send it on, and then make that other machine do something pretty scary. Or what is classic these days with data centers is people just want to record lots and lots of data. They just want to record all this stuff and just throw it away in data centers that may sit there for years. And then they're just going to wait till post-quantum comes along, and then they'll decrypt a lot. So that's store now, decrypt later, which is quite popular at the moment. But you can imagine the amount of storage you need for that, just storing all this stuff. So the best practice is to assume the adversary understands techniques used to hide the message. So security must be derived from some hidden information referred to as a key. So typically you have some kind of cryptographic key which will allow you to encrypt and decrypt the messages. One of the things that's kind of interesting about cryptography is that people sometimes say, oh, well, I've figured out my own kind of encryption system. I do this kind of really cool thing, and I'm the only person who knows how to do it. And, it's kind of my little thing that I do. And you think, oh, that sounds pretty secure. Nobody's going to get access to it. But it's kind of the opposite. You really need to use cryptographic algorithms that are basically out there and standardized. The reason for that is that if ever there's a vulnerability found in those algorithms, it will be highlighted immediately because everybody needs to know. And all these institutes that do these standards, they want to make sure that any vulnerabilities is out there immediately. So you must use the standards that are out there. People, yes, they know what they are, but it doesn't matter because it's all about the key that's hidden. And if there is a vulnerability, you'll find out straight away so you can change it and update it, etc. So trying to hide and have some really cool encryption system is often bad because you would never probably know if it was cracked. If both parties share a common key, we say that they are doing symmetric cryptography. So this is where one person wants to send a message to somebody else and they want to encrypt it and then send them the message. In symmetric cryptography, each person has to have the same key. Now that's a weakness because you've got two keys in the system and somehow you have to get the key to the other person. So there's weaknesses in that. But it's still, it's used obviously today because the methods used to create symmetric encryption and decryption are very, very fast. They don't need very big keys. About a 256-bit key is common today. And it's still very secure. It's been around. AES has been around for a long time. It's not been cracked. 128 is felt a little bit maybe old now. 128-bit key, but a 256, it's fine for symmetric cryptography. If both parties are unable to agree on a common key, so they don't want to share a key, before beginning communication, we say they are doing asymmetric cryptography. This is where you have two keys, a public key and a private key. Techniques for asymmetric cryptography are substantially slower. So Symmetric cryptography is used for some streams of data because it is pretty fast to decrypt and encrypt. Asymmetric cryptography is typically used for signing and maybe sending keys to another person. So, because they're quite complex and takes a lot of CPU cycles to actually encrypt and decrypt. So it's often used just for a one-off or starting a session. Okay, so asymmetric keys. So in an asymmetric system, you have two keys: the public key, which anybody can know, you publish it, anybody can see it, doesn't really matter, don't care. And you have a private key. So that's the key that you have, and you have to keep that very safe. If that gets out, everything is lost. So this is what we call the secret key or the private key. So they're based on a difficult to solve problem, which I don't need to go into, but the most common today is RSA. And the RSA stands for the three guys that invented it. And ECC is elliptic curve cryptography, which is they use smaller keys. And it tends to be easier to compute, so they're used a lot on microcontrollers and things like that. But RSA is still very popular because it's still being felt as probably one of the most secure. There's no vulnerabilities being found in the larger keys. Some of the smaller keys, yes, and they've been able to break as computing power has increased and improved. But if you use like large keys, it's still not being cracked. So as I said, you get a public and a private. So what's kind of strange about these keys is that either key can encrypt information which can be decrypted by the other key. So you can encrypt something with the public and the private can decrypt it. And you can encrypt something with the private and the public can decrypt it. So kind of like a bit weird. Either key can be used to sign some data which can be verified by the other key. However, the private key must never be disclosed. So that's your secret. And the really cool thing is the other person doesn't need this. He just needs the public key. So the other one is secret, which you talked about. So this one is both of you have to have this secret key. So you both have to keep it secret. So the weakness in a way is that you actually have to send it to somebody. One of the methods used to do that is you encrypt the key using asymmetric, and somebody else then can decrypt it with the public key. So you could decrypt this with your private key. So nobody knows your private key, so you decrypt it with your private key. And somebody could encrypt it with a public key, but then everybody could decrypt it. But if you do it the other way around, then it's just that person. Symmetric cycles were invented before asymmetric. Yeah, so the AES algorithm has been a long time, and it's been on small microcontrollers for some time. So let's have a look at a bit of a comparison. So the security level here is just to give you some idea of how hard it is to crack the key. So if you look at it the way you do it is you say 2 to say the 128 operations, which is like a brute force attack. So you'd need that many operations to crack a 128-bit AES or a 256-bit ECC or a 3K RSA key. So these keys, most people use these today, 248. The CIA secret documents, typically larger than 3K. And then these, I've not known anybody use these. These are like hyper secret, and this one is like crazy. It gives you some idea of how secure they are. And then this one, I put this in to show you the size of post-quantum keys. So you can see one of the reasons why people use ECC, certainly in microcontrollers, is the key size is quite small. So on a microcontroller, your resources are kind of restrained. So you don't have much memory, maybe have 2 meg of flash, maybe half a meg of RAM. So storing lots of keys could be a problem in much smaller devices. So it's much better to have like a 256 ECC key is kind of like the standard today. It's used in most stuff. We use it in our systems. It's very, very secure. There's no vulnerabilities being found. You can see the problem with PQC is the huge size of the keys. And this is one of the things that everybody's working on right now, as to how we can implement QC algorithms on, a small microcontroller. That's one of the things that we're actually doing at CQ. And then in the context of quantum computing schemes, they could be more vulnerable, like an RSA 248, which is seen as like probably one of the hardest today, used very commonly. But it might only need 56 bits with Shor's algorithm running on a quantum computer to break it, instead of what you see in the chart. So that's just an indication of what we're dealing with. You see.
So it's a good time to talk about the pizza.
Yeah, pizza time.
Pizza time. Let's count how many people we've got. 7, 12, 13, 15. So is there anybody with special dietary requirements? Yeah. Sorry? Vegetarian. Yeah, we'll always order some vegetarian anyway. So plant-based veggies and fruit is great. So I think, yeah.
Dairy free.
Sorry?
Dairy free.
Dairy free. I think if you take the plant-based one with the cheese on, that'll be dairy free, won't it? Okay. Thanks. I'll get on board with this.
So that's cryptographic keys. There's another thing that's used a lot, which is called hashing. So this is where you take plain text string, or typically a software binary file, and you throw it through a hashing algorithm. Again, these have been around for quite some time, and you get an output of a fixed length, depending on what the sizes of your hash. So today we use typically a SHA-256 hash. So the 256 means that whatever size this file is, I don't care what size this is, but if you put it through a hashing algorithm, you will end up with a 256-bit number. So what is the point of that? Well, with a hashing function, if you would take this large file, hash it, you get a code. If you then were to change one bit somewhere in that file and hash it, the hash number would be completely different. So this is used for verification that you received the correct information and it's all there, i.e. nobody's modified it, while it was sent to you. So if somebody's going to send you some software over an encrypted link, they will typically send you the file, probably encrypted, and then they will do a thing which is called signing it. So signing it will mean they will actually have taken the software. Once you've decrypted it and you can see it, you can push that through a SHA hashing algorithm. They would have done the same. They'd have got a number at output, and then what they would do is they encrypt that number using their private key. So they were the person. So then that person who sent it to you, they have the private key, and they've signed that word, so it was definitely come from them. So when you get it, the code, you decrypt it, you hash it as well, and then you check that the hash number you got is the same as the hash number they sent you. Now you know that you've got every single bit of this file. So that's used for and we'll call integrity. It's also actually used in the banking industry, where somebody you may say, well, I don't remember sending you that money, or approving that money. It definitely wasn't from me. Well, if they sent you the file and they hashed it and they signed it, then you can prove that they sent it because, well, it was using your private key. You signed it cryptographically, so it absolutely came from you, and they cannot deny it. So that's why the financial industry uses it. So these are some different SHA. SHA-1 is not used anymore. That was cracked a while ago. Most people use 256 or 3v4. I've seen some systems using 512. So basically, that's all SHA-ing does. So it's used for checking the integrity of some files, essentially. So some of you guys from IT, you must know what a certificate is, I guess. Yeah. Have you actually looked at the anatomy of it, what it's actually inside it? Like that. So when you open a browser and you connect to Google, they swap certificates. And what it looks like if you decrypt it, is it looks like this. And inside, it'll have the actual public key of, say, Google. And then it will also give you here the signature. So what you can do is you take the certificate and you have a look at who sent it. So you can say, okay, yeah, it came from Google, blah, blah, blah. Looks like it's from them. Company details are right. Okay, so now I need to check whether they actually done that correctly. And this hasn't been interfered with. So what you do then is you'd extract the public key. You would decrypt this signature. And that signature would give you a hash number, a 56-bit number. You would then hash the certificate and compare the two. They were the same, then the certificate did come from Google and they signed it. So that's what we do with certificates. It's kind of like a passport. So when you send somebody a public key, say this is my public key, I've got the private, and if I send you anything, you can decrypt it with the public one. But sometimes you may not know whether that's actually come from that person, or is it actually their public key? So usually you send a certificate which has the public key on it, and you sign the certificate. So then they know, oh, right, yeah, that did actually come from you because I can prove that you signed it. So that's typically how public keys are sent around in different entities. What typically happens is a certificate authority. So this is a known company, DigiCert was one, or VeriSign. These companies, they actually will verify that the public key has come from that particular company. So typically they find out, you know, where does Google, where are they, look at their address, go and see them, talk to them, and they make sure that the certificate is correct. And those are the ones that are always in your browser. It allows a little shield to come up that the certificate has been verified. So we use it quite a lot in microcontrollers and connecting to the cloud, certificates are used. I wanted to show you this one, and don't worry about it, you can have a look at this later, but this, to me, when I first saw this, is utter magic. It's the way two entities communicate to each other over an encrypted link. So effectively what happens is you've got a client and a server, and they want to talk to each other, but they want to make an encrypted link. So one way to do that would be to create a key somewhere and then pass the key over to the other side. And then you use the same key. But of course, you've got to somehow get that key over to them. So how do you do that when you're trying to fix this encrypted link anyway? So you do that by using this awesome technique whereby the client and the server, what they do is they generate an asymmetric key pair, so a private public key pair. And they just use a random number generator and just generate a random number, put it through a number generator and make a key pair. So you have a public and a private key pair. Then what you do is the client, so both do the same. So nobody knows what they are. And then what they do is the client and the server, they actually tell each other their public keys. So they put it in a certificate and they send to the client, here you go, there's my certificate. And the client sends it to the server. So the server just has a public key, and of course it's key pair. And this client has the server's public key and its key pair. And then what they do is they take their public keys and their local private key, and they put it through this algorithm, and out pops a shared key, which is the same. So they swap public certificates, and then using this algorithm, just with their private keys, they generate their own shared key. So they actually don't have to swap it, it just appears through this algorithm. It's absolute magic. And the guys who developed it were brilliant, but yeah, search it up and have a look how it's done, and it's called elliptic curve integrated encryption system. So it's a brilliant way of setting up a encrypted link with another entity by just swapping asymmetric public keys. Absolutely awesome. So this is just a diagram of how it's done. So you can see here, you send the ephemeral public key. So this is just generated, and if you broke the connection, which is often happens, say if you're talking to Google and something happens to your Wi-Fi and you drop it, when the connection comes back up again, they do this again. So they just generate another key pair and swap it. So each link, it's just virtually impossible to hack. And then this MAC bit is just simply part of the hashing algorithm. So basically you can verify the integrity of the data that's been sent as well. Yeah, really cool. That was totally impressed me. So roots of trust. So a root of trust is a small area of typically a microcontroller or processor. Oh, sorry, secure boot. Secure boot. So this is where your a good way for hackers to get into a system is when you reset it. You know, the system that microcontroller jumps to some memory somewhere and starts running the program. So if you could inject your code, you reprogram the memory with your software, then obviously you can take over the machine. So to stop that, most microcontrollers today would have a secure boot process. So this is whereby the chip has actually been designed so that when it boots up from reset, it doesn't just jump to 00 and start running code. It actually jumps to a bootloader inside the silicon, which has been programmed or wired into the silicon by the vendor, the manufacturer of the chip. So nobody can get to that piece of code. You can't get at it. It's just hardwired. And what happens is that process jumps to the ROM inside the chip, and it goes through a bootloader process. And what that does is it basically looks at a memory area, so starts at a certain location, which is again programmed into the ROM, and then it will check what's in that area, and it will hash the code, and it will verify that hash against a hash that would have been burnt into its what we call one-time programmable memory. And if that code in the memory, the hash compares to the hash it's got burnt in its chip, in its silicon, then it knows that bit of code is good. So then it will jump to it. And secure boot means that there's nothing that can interrupt that process. So you can't like have a debug mode where you reset it, and as it's jumping through the ROM, you can kind of stop it and then start putting, inject memory copies or something like that into the chip. It's what we call an immutable process. So every time you reset it, it goes through that same sequence. So then the question you ask is, well, hang on a minute, that code that it checks it against, how did that get in there? Well, then that's typically down to the person who's bought the chip and is making a connected product. During manufacturing, he will have burnt that, what we call a key, into the chip, make sure that only he can check that code. And typically it's also a signature for that code. So you could update it and check the signature. So secure boot is a process that ensures only trusted authorized software to be executed during the system startup. So it checks the integrity and the authenticity of the bootloader. Operating systems are the critical software components checked before it's loaded. So basically, the secure boot builds on what this root of trust. So the root of trust again really is this area that's got this code in it, which is what you're checking again. So that's got to be hidden securely in a root of trust area. Without the root of trust, the integrity of secure boot cannot be guaranteed. So you can't put that hash that's going to check a signature. You can't sort of just put that in normal memory somewhere. It's got to be in an area of the chip that can't be changed or anybody can access it. So that's what we call a root of trust. So root of trust is a set of unconditionally trusted functions. So that's a microcontroller that will run a set sequence. Some examples here are on some other microcontrollers like Trust Zone you may have heard of. An ARM thing when you can only execute code in a secure world area, they call it. So it's where you could store cryptographic keys. A ROM-based bootloader is absolutely important. You must have that. And that will authenticate the software image. And then typically microcontrollers have some kind of JTAG port to do debugging, and that JTAG port must not be able to interrupt the bootloader process. So that's really what a secure boot mechanism is. So if you want to make a product, certainly with the CRA standards moving forward, you have to have this function inside your microcontroller. And typically, they're quite complex to get working. So this is just showing you how the sort of microprocessor starts. It will check the initial bootloader, verify that it's good and been signed. And then typically that next bit of code is what we call a second stage bootloader. Because this bootloader you may want to have under the control of, say, somebody further down the supply chain. So you'd want them to be able to sign and check that area. And then eventually you'd load an operating system, and that typically would be signed, and then the operating system would have apps that you can download. You may want to sign those as well. So this is what we call a chain of trust, where each function is checked first before it's run, and then that function may check the next function. So microcontrollers are manufactured with the root of trust. They've got this hard-coded public key or hash of the public key going into the silicon. Usually the silicon manufacturer owns that bootloader key. That's one way of doing it. Or typically they leave it open so that the next person in the chain, the person making the product or writing the first level of firmware, they can actually blow or program the one-time programmable area and put their own key inside. So they now own the capability of that device to check that the software has been signed correctly. So again, like I just said, the ROM code fetches the hash of the public key. So this is a more complex way of doing it. So you can check the code that's been downloaded to the device. Typically that would include a public key in the software, because sometimes you don't necessarily want to store in that OTP area a big public key for checking, because again, that's a lot of memory, and microcontroller companies don't want to program, don't want to use a lot of ROM area, because that's going to take up silicon. So instead of putting the public key, program that into the one-time, you program the hash of the public key. So then the software would actually be sent with the public key, and the boot ROM would actually check the public key, hash it, and compare it against the hash in its root of trust. Now, oh, right, yeah. So that's definitely the public key I must use. And then it uses that public key to verify the code. So it gets more and more complicated, but that's typically what we're doing. Private key is used to sign software, of course, because you have to know that it's come from a trusted source. Usually this public key is kept in, say, the metadata of the firmware that's sent. The key related to the chain of trust. So these keys that you have to program into the device to do this immutable boot have to be done either by the silicon manufacturer. So somebody like Scilabs with their Secure Vault, which I showed you earlier, they actually can do that for you. So they can program a key into the device and then ship it to you. So it's a blank bare metal device, but it's got the key inside, so you know that that bootloader is owned by you, and they'll give you the key for it. So you can sign that software, and that device will boot only from software from you. They can do it that way, or they can typically they leave it open, and then they get shipped to you. People buy these microcontrollers, and they give you instructions, user manuals on how to program that key so that you can do that yourself. So typically, I mean, here's one used by, I think this is STs, I think. So they typically can provide a smart card. So they'll put the keys on the smart card for you, blow the chip, and send it to, say, the OEM here would be somebody like Bosch, who's making, say, a washing machine or something. So they would send them the smart card with all the provisioning software on it to tell you how to program those keys. They would go to the Bosch's design center. They would configure the smart card. Typically, it'd be used somewhere on a production line, but they would configure it for you. They would then ship that smart card to their manufacturer. So Bosch don't necessarily build stuff themselves. They build stuff all over the world. So somebody else, a third party, has to program those keys in. So the reason they use a smart card is because obviously you don't want these guys to know what those keys are, right? And this is where it's important to have security because of these supply chains. So they ship the smart card to the contract manufacturer. They have a programming system whereby they're programming the chips as they're going down the production line. So they're injecting the keys from the smart card into the chips, so that the contract manufacturer never sees them. And during that process, a certificate is generated, the one with pop a key on it. And then that would get sent back to the OEM. And in the case of wanting to connect this product to a cloud service like AWS or Azure, they would send, the OEM Bosch would send all the certificates to AWS to say, all these devices have been made by us, Bosch. You can see it, we're on the certificate, and here's the certificates and all the public keys for all these devices. And then these devices can now get put in a washing machine, taken home, plugged into your network, and you can control your washing machine from your mobile phone. Really cool. And this is all the process that you go through.
Excuse me, so not much the same processes whereby Windows can identify the CPU on which you've installed them.
Yeah, they do it in they have what they call a TPM typically on most laptops, and they've been pre-programmed by Microsoft. Inside there, they'll have keys and certificates, but they're getting quite sneaky in that they can actually match the system to your actual laptop configuration, I believe, and that's usually held as part of the TPM. So they have this little chip that can look at data and check signatures and check its integrity before it actually allows Microsoft Windows to boot. Yeah, they're getting pretty secure on their stuff. So this is typically how it's done today. It's quite expensive because you need to have equipment in the contract manufacturer. Typically, this is cordoned off the area that they're programming the devices. They might be in a secure room or use secure programmers. The programmers need to be connected to what we call an HSM or a hardware security module or this smart card system. If they're generating keys in the factory and injecting them, which can be done, they aren't necessarily sent from the OEM. Then you need an HSM, which again is expensive. And it's inherently insecure because you've got somebody else, and they're not seeing the keys in this case. But in the case where you've got an HSM where they're injected into the chip, they could see the keys going in, depends on what the mechanism is. On older chips, the keys would have to be in the clear because you'd send them over a small JTAG port. But in the newer stuff like the ST, it's encrypted. But you've got the keys in the HSM, the key is in the chip. So you've got multiple copies of the keys, which is inherently weak, you could say. So how can you get around that sort of thing? How can you get around of having to inject these keys, having to manage keys? So you could use PUF technology. So there are two different types of PUFs. They changed the wording recently because they didn't like the use of the word strong PUF and weak PUF. But it kind of like, what? Then why are we talking about this? So I just want to explain, they're now called confined PUFs and center PUFs. And we were upset because we've got a confined PUF. So what is this? So a PUF is a physical thing, in our case inside a silicon chip. And what it does is when you challenge it, so you say, here is a function, give me a seed or a random number. I challenge you, give me your identity. The PUF will provide you with its identity, which could be a number, just a straightforward number. In a strong PUF, that, say like a MEMS, like a pressure type piece of material, you would say to the PUF, right, what's your number? I'm number 7. You challenge it, yeah, number 7. But if you kind of like squeezed it or something like that and you challenged it again, it said, oh no, I'm 8 now. So that means that there's kind of like a third input that could actually change what the output is. We have a confined PUF, which means whatever you do to it, it always gives you the same number. And this is what we use. We have an array of 64 by 64 transistors, and basically this is what the fingerprint looks like. And this is used for identity of a chip. And the way we do that is you put basically a PUF on your silicon chip, like a microcontroller or processor. And what it does is when you ask it for a seed, which is just a random number, it can give you up multiple seeds. So you can say, give me seed 1, and it gives you a seed which could be 256 bits long, 512, whatever you like. And every time you ask that PUF for that seed in slot number 0. It will always be the same, always. If you put it in a silicon chip, what you can then do is you can take that seed and you can put it through a key generator. So you can use the random number effectively to generate a key pair. All right. So now what you've got is you've got an asymmetric key pair based on seed 0. And what that means is when you challenge this device, you say, okay, what's your identity? And you send it say a random number. You would encrypt the outside entity, would encrypt the random number using the public key, because of course this is public, everybody knows it. And you'd send it to the microcontroller that had the path. The micro would extract the seed from the path, create the private key, decrypt the challenge, the code that's been encrypted, decrypt it. Maybe sometimes they just add a date stamp or they add something else to it, slightly modify it. They could encrypt it again and send it out, and then the outside entity would decrypt that then with a public key and know that, wow, yeah, this guy's got the private key, so he is absolutely the guy I'm talking to. And this is the basis of our technology, in that you can actually prove that you own the identity you state that you have. So you say I'm number 8, I'm microcontroller number 8. Obviously, it's a much bigger identity. But say I'm number 8, and that microcontroller can always prove that it's number 8 by using this technique. It'll always get the same seed 0 out, create the keys, and do it. Now, so it's kind of, okay, well, what's so clever about that? Well, what's really clever about that is nobody knows the private key. Nobody. The only person that knows the private key is this key generator for a few nanoseconds as it's generating the key. So no outside entity knows the private key. So wow, how safe is that, right? So that's the basis of it. So you can always prove identity. How do we do it? We have an array of 64 dual transistors, like this, a left and a right. And we have an unbelievably accurate analog circuit that measures the quantum tunneling currents across the silicon oxide layer of the transistor. This is an actual picture of the silicon oxide layer of transistor. So these dark patches are actually atoms. Okay. And we measure the quantum tunneling current that goes across here. Obviously, it's incredibly small. And to give you some idea of how our circuit is, so we've patented this circuit that measures the current. It's accurate. Give you some idea of how accurate it is that if you were standing on Pluto, you would be able to measure a meter ruler on Earth. So that's how accurate it is. And what we do is we measure the quantum tunneling current of the left one, and we measure the quantum current of the right one. And depending on whether the one is one higher or lower, it's either a 1 or a 0. And we have an array of those. And you get this pattern, what we call the fingerprint. This is the fingerprint of your device. So it's inherently random, because no matter how the semiconductor guys claim they can control the thickness of the silicon oxide layer in your transistor, they can't control it to the level of quantum tunneling currents. So the 1 or the 0, the randomness is dependent on, obviously, this change in the thickness of the layers, but also it's based on the interactions of these atoms and the way they're constructed, what we call nanostructures. So the quantum tunneling current is based on how these atoms interact and the thickness of the silicon oxide layer. And what that means is that if you have a reasonable size quantum computer, you wouldn't be able to figure it out. It's a quantum effect. Unlike other puffs that are out there, which is based on an electrical sort of threshold effect, which you could kind of model it. So yeah, so we basically scan all these transistors and provide the microcontroller with a seed. So this is where typically our puff sits. In a system, you get the seed and generate the keys and provides identity. It's really straightforward. The CMOS transistors, it had a very high entropy. We've done all the testings for it, and it has it's not affected by side channel attacks. Connecting to the cloud. See, I'm a bit behind here. Connected to the cloud. So this, I just put this up to show you how difficult it is to connect to the cloud. You need to have certificate. But if you're building a product with a microcontroller, typically what you do is you ask the device to generate a cryptographic key pair inside. You then ask it to request a signing request. So it generates a like a certificate request. That goes to the device manufacturer, they Bosch again. They would receive the CSR, generate the CSR, pass that over to AWS, who would take the certificate signing request. This is a TLS encrypted link. They would then sign the certificate based on their root certificate. They would send it back to Bosch. Bosch would then take the certificate and put it inside the. It's a nightmare to do. AWS, they have a root certificate, which you can go and have a look on their website if you want to have a look at it. So all their certificates are rooted on this certificate. So they have this intermediate one, and then yours is taken off the certificate. So that's their chain of trust. So you can always take your microcontroller, have a look at the certificate, and you can always go right back to Amazon's root certificate, which was signed by an entity, so you know it's from them. So it's complicated. What I'm trying to get to is it's very complicated. So this, I showed my boss this. He said, "You're not going to show them that slide, Amy." I said, "Yeah, just let me." So you remember that awesome algorithm I showed you earlier, which is just magic. This is how it works. So basically, it's what this is saying is you swap the public keys, you generate the shared secret, and then you start exchanging. That's how it works. It's really cool. How does it work in post-quantum? It's different. So in post-quantum, the client sends its key to the server, and then the server actually generates the shared secret. But then it encrypts it and sends it to the client. And then the client decrypts it and they start using it. So you see the difference? So this one, there's no key shared apart from the publics, which doesn't matter, doesn't matter sharing the publics. So they're shared and then they're generated differently. So the shared secret doesn't pass. But in PQC, what we call MTLS right at the moment, called key encapsulation, it's actually sent to the client. But it does use a post-quantum algorithm. It's good, but it's a slightly different technique. So the problem, I think, is that there's no algorithm yet that can sort of generate the same shared secret that I'm aware of. So yeah, that's that. Post-quantum processes. So these are, they announced in December 2016 that we needed to have post-quantum cryptographic algorithms. 82 candidates were submitted. Took quite a long time for them to go through and check that they were okay. 3 only made it through. And one key encapsulation method and 3 signature schemes. I don't know if you heard, but it's probably about a month ago, not long, a few weeks after they released algorithms, 2 Chinese mathematicians said they'd cracked it. They cracked one of the algorithms. Absolute panic, complete panic. Big checking, evaluating, white papers, and they'd actually made a miscalculation in their white papers. We're good. So these are the ones: Cyber, Dilithium, Falcon's kind of a new one because this one looks like it could be a bit faster. I was trying to get something that helped you. Have any of you looked at post-quantum lattice? Yeah, I might be able to teach me that. So bottom line is this is saying a 2-dimensional lattice. You have 2 vectors that's part of your description of the algorithm. And the 2 vectors are basically describing a lattice of points. And the algorithm, which is the hard to find bit, is what is the nearest point to the origin based on these 2 vectors. So this is just 2 dimensions. So this presents this array. So you've got to try and figure out, well, what's the nearest? If I had a circle at the origin and I started growing out, what was the first point that touched the circle? And that's the shortest vector algorithm. This is 2 dimensions. For dilithium, the keys, the vectors are 1,000 dimensions. So, this is kind of trivial. I mean, this is hard using a Euclidean equation, but imagine with 1,000 dimensions, parameters. Anyway, that's kind of how it works. I put this chart up and get it on the web. It's basically what they did is they took a standard microcontroller, a Cortex M7 running at 216 megahertz with the 64-bit FPU, which is the important bit, because they really wanted to test the Falcon algorithm. And these are the times it takes to generate keys, etc. So you can see how many milliseconds it takes. So this is like 1.5 seconds for this one for a key generation. So if you think about it, if you're trying to talk to something, you're going to have to wait 1.5 seconds before it generates the key to start an encrypted link. And that's off quite a small microcontroller actually, so it's not too bad. So one of the things we're trying to do is improve on this. There's some open source code which you can run on microcontrollers and verify how this works.
It's not taking to crack.
Yeah, I mean, hundreds of times the age of the universe, I think.
Right.
I just wanted to know, most people use OpenSSL for doing their key generation and management, and use it on their laptop. The OpenSSL 3 does support some quantum algorithms, and then there's the Open Quantum Safe project, which you can have a look on the web. So these are the type of things an engineer would need to do, generate random numbers, generate signatures, of course, with software, do over-the-air updates. My point with this is that you're doing this on a laptop. So I'm going to generate a key. OpenSSL would generate and just put the file on your drive. Your private key would be on your drive. So the problem is with developing software like this is that you want to make sure that your microcontroller or your product actually works with OTA over-the-air updates. So you sign some code and you send it to the device, and then it all gets working. Then you do some field testing, and the key's still on your laptop. Somebody says, "Well, that isn't very secure. Best have the manager have the key." So you generate another key, or the manager does on his laptop, and then he's kind of put it in a folder called secret keys. And this is generally what happens, right? So and then the manager gets hit by a bus. So they got all these stuff in the field, they can't update them. It's a nightmare. So the problem in the market is, how do you control all these keys and all these certificates easily? And that's really where we come in. This is just showing you kind of the supply chain and the problems that you have. So you've got like a piece of equipment down here manufacturing, it's maybe an edge Linux device. It'll have either a TPM in it or a secure element. It'll have secure boot, hopefully, inside. And once you've manufactured it, you're going to have to sort of register it with some kind of server, as you saw, generate some certificates, and they have to be sent to the server, and it has to be stored. They're typically stored, either stored in an HSM, somewhere in the cloud, and they have to be registered with authorities, etc. And then as you deploy it into the field, so somebody goes to Comet, they buy your washing machine or whatever. Then you have to generate all these certificates and keys and validate that it's the correct one and it can talk to the right application in the cloud. So the certificates all have to be managed. Obviously, you have to enable secure boot to do all this, so that's complicated. And then during the lifetime of the device, you have to manage all these certificates, revoke them if they've gone out of date, make sure they don't go out of date. That's a classic one where you put all the certificates in here and only give them 5 years. You think, 5 years, that's fine. And then you realize after 5 years, all the units have gone down in the field, customers are ringing you up, going, "Oh, my washing machine doesn't work anymore." So all this kind of stuff has got to be managed, and it's very difficult to do. And then when you retire the product, you have to kill the certificate, etc. So this is kind of the sort of supply chain and the management that you have to deal with. And one of the things we're trying to do at Crypto is kind of manage this. There's a lot of guys out there that claim to do sort of device lifecycle management, but to certain bits, they might be a device a certificate authority, so they might generate certificates for you. They might generate them and send them to you, and you put them in the device. So that's kind of a very small part. The semiconductor manufacturers will help you doing secure boot and things like that, but they don't really want to deal with the certificate side. That, you know, that's up to you. Any example projects they have on their websites to say, oh, this is how you connect to AWS. There's a lot of them, but all the keys and all the certificates are all in clear memory. They don't really want to deal with, you know, how they're kept hidden and stuff like that. And then some companies do quite a bit. Memfault is quite popular, and P-Factor, Fidelski, they have a system, and Device Authority. There's some of the people out there, but they tend to kind of stop. They'll do some of these functions. Some of them do all of them, but typically they stop at the API. So they just give you API calls in your microcontroller. They won't help you sort of implement secure boot mechanisms, use secure elements, TPMs and stuff like that. They kind of stop there. So there's all sorts of guys out there. These are just some of the standards that you need to comply with. Some of these are automotive, but pretty much all of them are going to be covered by CRA. So a bit of sales here. So we have a device called QuarkLink. You can talk to it from a web server, or you can talk to it over CLI. It actually generates all the public infrastructure, so all the certificates it manages for you. You don't have to worry about it. You can get an instance, you can go to our website, register, you get a free QuarkLink. It can manage up to 50 devices. It'll give you the root certificate, has its own root, it's generated, you can read it, whatever you want to do, but we try to sort of keep it away from you, that you don't have to touch it or manage it. It's all done automatically. We can talk to the device over Wi-Fi or internet or whatever. We support different MCUs, ST, Renesas, etc., MPUs from NXP, TPMs, others we support like FreeRTOS, Azure RTOS, Linux. And we do, the cool thing is we actually do all the provisioning for you. So we can program the bare metal with the keys for you from the tool. And we can give you templates to allow you to just start. You can get our template, and then you can just add your code, and all the secure boot and the management of the keys is kind of handled for you in there. And we can even program the device. So all that attestation stuff is done automatically by the device. So we can connect to AWS, etc. And we can do over-the-air updates. We are currently working on container management, where you can drop a container on your edge device, and that's encrypted and secured, etc. But we can kind of do all this. So, in summary, PQC is important. As for when quantum computers are available, that's 20 years' time. It's about 20 years they'll be here. And I've heard that for the last 30 years. It's still a long way off, actually. But the PQ algorithms are out there. There's these certification guys, they're working on validation and testing for them, test vectors. FIPS is kind of high-end standards and certification standard. So you can actually say that you've got a product that's PQC ready. You can send it to test houses, and they'll test it for you. Our QuarkLink is PQC ready, so we can, the QuarkLink, the cloud end is PQC ready, but obviously there's not many things that we can talk to that are PQC ready. We're working on that. So there is, of course, a transition period. You can't just say like, oh, okay, tomorrow you're all going to have PQC algorithms, because again, it's that same problem. But in the case of pumps, you can't go and retrofit pumps in a day. So there has to be like a transition period, of course. And there's like hybrid schemes where you can do pre-quantum schemes and do it in parallel with your current schemes. Yep. Of course, with PQC algorithms, they're invented new side channel attacks. And you'd expect there's always somebody trying to crack them. And the requirement for, so the signature algorithms are quite complex, and the signatures are very big. So there's some work going on now, started last year, where they're trying to make the algorithms that have much smaller public keys. They're just huge. So they're trying to cut down on that. So there's an awful lot of work going on in the background to implement PQCs and get them to work on IoT devices. Emil's gone, so I'm not sure how I am for time. But I've got to show you a quick demo of our stuff. Time.
You have about 20 minutes.
Oh, go on.
15 minutes.
Any questions, by the way, while I stop sharing?
I got a question. You mentioned the size of the keys will be significantly increased in the post-quantum era. Is that because the code breaking attempts is still based on combinatorics, the same as today?
No, I think it's because of the amount of information that you have to provide to do these multi-dimensional lattices. So there's quite a bit of information that's in the, I think it's the public key, it's maybe higher, maybe wrong there. So I think there's a lot more information needed to create the lattice and then set up the hard to solve problem. So that's one of the reasons, as I said, they're trying to cut down on the size of that, because that's, that's what's generated from using these particular algorithms. I think that's what it is.
I mean, the code breaking techniques in the future is still relies on combinatorics, because this is the time consuming part in the day.
Yes. I think you mean,
Yeah, because in the future a quantum computer will be very fast, so we have to increase the size of the keys to keep them to outrun them in breaking. Is there any mechanism we can employ quantum entanglement, things like this, and to people two chips always entangled together?
Oh, yeah, that would be
that would be virtually unbreakable.
Yeah, that would be cool. Yeah, quantum entanglement would be quite something if we can achieve that. Yeah. Yes, that would be something else. Wouldn't it? Let me show you this. Okay, I'm just going to show.
Quick
Yeah, sure.
And you say categorically that quantum computers are a long way off, but I'm sure you know that they do exist, of course, yeah?
Oh, yeah, they exist, absolutely.
Okay, so when you say that it's a long way off, in what terms?
Oh, in terms of actually doing anything useful.
But
so,
you can get a 90-qubit quantum computer today to do low-level decryption and analysis.
Yeah, low level. So it's always usually to do something reasonably simple. Because they're still having to deal with the errors, right, from quantum computers, and they're still kind of figure that out.
Yeah.
Which is not an unsurmountable problem. So I can't remember now what they said they've cracked. Maybe they've maybe cracked some older algorithms.
It's modern Cypress they've done, but as you say, the problem is like doing it routinely, repeatedly.
Absolutely,
it's very difficult and expensive.
Yeah.
So
practically, and
in a practical basis, it's still difficult, but I think it's not as far as you said like 20 years ago when they were talking about this. It's no longer just 20 years, it's more like a lot less than that.
Call me in 20 years.
I'll call you in 5.
No, I'm great, if
I just wanted to kind of like emphasize the difference that there is quantum computing available today.
There is
that can do cryptanalysis, albeit at slightly more cost than being the financial cost of setting these systems up than your classic encryption systems based on classic cryptanalysis methods using GPUs and even CPUs. So yeah.
Yes, it has been done, but it's in a lab with a huge piece of equipment, but it's absolute zero. Blah, blah, blah. It's not really something you'd like, a hacker.
That raises an interesting point as you mentioned the absolute zero part. I was intrigued by your slide about the quantum effect of the two things speaking to each other. Now that's at room temperature, isn't it? How does that work?
So
you demonstrated one part. Was it the where it's generating? It was like a chip that had transistors on it.
Oh yeah, so that's how techniques.
That gap there, you're using a quantum gap there.
No, so one of the problems that's been around in the semiconductor industry for some years now is as the silicon oxide layer on the transistors got smaller and smaller and thinner, what they have always been trying to do is make sure that when the transistor is off, there is no current, right? Right? That's very important. But what they found is as they get smaller and smaller and smaller, there was these leakage currents.
Yeah.
And they didn't understand why they were and where they were coming from. And it turns out that as you get smaller and smaller, the barrier, the energy needed to cross sort of a barrier like voltage or whatever to get an electron across. You don't necessarily have to have like an Ohm's law to get that electron to go across. Randomly, electrons will flow across, and and as you get smaller and smaller, it actually becomes a current. You know, it's in the hundreds of picoamps, but it's a current. And when you've got a transistor, a chip with 1 billion, transistors on it, an Intel chip, it's a lot of current, right, that you're burning. They get hot. And it's so now you've got the FinFET, right? So they're trying to fix it by designing these transistors, exotically, to try and get around the quantum effect. Well, we measure that current. We just measure it.
Okay.
Yeah. And the point is that its value comes from. There's a big equation. It comes from how those atoms interact and the thickness, obviously, of the layer.
We need to get on.
Yes, we do.
Food's actually arrived.
Okay.
We're trying to keep it hot, but
Yeah. Do you want to?
interesting.
outside
This is
and-
what we can see now on the shared.
Yep, you can. I was going to just show you how.
It's not up there.
Oh. Oh, right. No, I only shared it on the. Oh, right. Okay. Got to share both. I shared it as. Why is it not up there? That's weird. Just an application window.
I think you just need to
Yeah,
duplicate.
I've got it.
That's the word. Duplicate the place.
Yeah. Nope. Don't know what they're presenting.
But maybe if you just exit from the PowerPoint demo, you'll be fine. Huh?
Success. So this is our SaaS platform called Corpin. I just wanted to show you how it can be used to develop a product that you want to connect to the cloud, taking into account all the stuff I told you earlier about enabling secure boot, managing keys, etc. So for those of you who are on Zoom remotely, I do have a small microcontroller connected over USB to my laptop. It's an expressive device. We typically use it for demonstration. It's an ESP32. It's a Wi-Fi module. It's just a standard board that you can get from Mauser, RS, whatever. This is a blank board, and we use this for demonstration, but we can support other microcontrollers, as I said, and SAS, etc. So you can register for one of these Corp links today. Just go to corplink.io and you can register one. You get one basically up here on the URL. You just get your own URL and Corp link, and you could buy an ESP32 from Mauser, and you can make a connected product with it really, really quickly. So when you get your Corp link, you will get a root certificate. You can see it here if you want to. That's what it looks like. So, I showed you that certificate earlier on the slide. If you decrypt this pen file, that's what you will see. You can see it's signed by us, and it's signed by your particular Corp link. So that's the root certificate that's used for any certificate that we're going to inject into this device or create. So they're all linked to this Corp link. You can create signing keys, etc. I've got a key here, which I've generated. I can only, in this evaluation version that you get for free, you can only create one. I won't delete this key because it's one I use for demonstration to other with other boards, and those boards, once I program them, of course, are permanently for the rest of their life linked to this key, right? Because I've enabled secure boot. If you look at it, you can see there's the public part of it. It's a 3072 size key. And that's the one I'm going to use to blow into this device and enable secure boot. So that's the HSM side of it and the key and certificate side. Devices. So these are all the devices that this Core Link is controlling and managing and handling all the certificates. Inside the batch of devices is the identity. Remember I said that each device ideally has an identity, and I said, you know, I'm number 7, number 8. Well, we use a 256-bit code here to prove the identity of the device. So I've got these devices I had before that this Core Link is managing. So before the Core Link does anything, it will first challenge that device. Are you this identity? It will send it a challenge. It will encrypt it, send it back, and the Core Link will say, once it's decrypted, yeah, okay, you are that identity, and then it will connect to it over a TLS link. So these are just batches, because maybe I've got some fridges, some washing machines, they're in different batches, right? And I want to send them different software, so that's why we have IoT hubs is the different things I want that device to connect to. So in my Bosch washing machine, I want to connect maybe to a certain washing machine account. I want to connect my Melee to a Melee Azure. So in IoT hubs, if I create an IoT hub, I give it a name, and then you can see I could connect it to Azure, AWS, or just generate an MQTT broker. So it just means you would input your AWS or Azure account, the login and the secret key to get to the account. Because Core Link needs to know that to connect your device to that cloud service. So all that cloud service stuff you saw, the Core Link would do that in the background. So what I want to do is I want to program this device. I want to use it and connect it to this Core Link. First thing I want to do is you'll see here I've got some S2 devices. If I delete that. I just used that earlier. But what I'm going to do is I'm going to create a batch of machines. I want to use default policy. That is, well, how long do you want the certificate to last? What's the validation period you want? And I'm going to generate for it. And what do you want to connect to? So you remember I showed you the hubs. Inside the policy, it's the hub that you want to connect to. So for my washing machines, I want to connect them, in this case, just to the MQTT broker in this particular Core Link. But I could have entered an AWS account and just selected AWS in there. I just want to do the default, which is policy, which is them. I won't load any firmware yet. The signing key I want to use is the key I've generated. So it's going to use that key to put in that device. So that's the batch created. So you see I've got my washing machine batch. So now what I want to do is create a provisioning task to actually start programming these boards to connect. So it's I'm going to call it wash provision. What is the type of device? So here, you know, we'd have all the devices that we'd be able to connect to. This is a ESP32S2. Now, what sort of the software I can put in it is 2 types. One is a release version, which is not something I want to put in here, because if I put the release version in here, this device would be completely forever fixed to this Core Link and the software for it. So I want to be able to use it multiple times for demonstration. So I'm going to, and maybe during development, you don't want to blow the keys off this the first time. So there's a thing on capability of this device where it uses virtual fuses. I'm going to use that. And when I provisioned it and programmed it, could you please make it link to the washing machine account or batch? So that's my provisioning. So now to provision it, it does need to communicate with the Core Link over Wi-Fi. So my hotspot is still running. So I'm going to say, so it's going to say, what network do you want me to connect to in order to connect? So obviously the local network I've got my mobile phone. which I can remember the passwords for. So it'll now program that SSID into the device, start provisioning. So it says, okay, I'd like to connect to the device. So it's connected to my port on here. So yeah, that's the device. Start connecting to it. And now it's going to start building the firmware, the secure boot firmware, etc. And it's going to start programming the device.
Silly question. Is that being built somewhere else, or was it on this laptop then being pushed out?
Well, it's it's not actually being built now, it's just being uploaded from somewhere else in the back end and then brought into the laptop. Yeah, it's not being built yet. We have the capability whereby you can upload your own software that you want to program into a device, and the Core Thing will sign it for you and put it to the device. But also we have got mechanisms whereby, say you were using something like Platform IO or VS Code to develop your software, you can actually commit it to your GitHub or whatever you use. It will commit it. It will then, we have a YAML script that we can provide you, which come with our templates, which basically will run, they will build that code, they will sign it, no, they will build it and they will send it up to your Core Thing. So you just tell it where this URL up here, Core Thing. Yeah. It will send it to the Core Thing, and the Core Thing will sign it for you and send it to the device. So it's great for development. It's just one.
Yeah, very cool.
Really cool. And it's and the great thing is, you see, you don't have to worry about who's got the keys, right? Though that key, my key, that's somewhere in the cloud somewhere. I don't know where it is. But it's not on my manager's laptop. It's not on my laptop. It's not at home on a hard drive. It's handled by somebody else. So all that hassle of key management is just gone. You wouldn't do this round loop thing, on your very first development. You'd first get your product working and stuff like that, and then you'd start looking at the skill group. Anyway, so it's programmed it. It asks the device to generate its own identity. So we don't know the private key for that. And here, this is its identity, and it's put it in the washing machine batch. So if we go to devices, you can see washing machines here. If we look inside, it's actually got the batch, which has been loaded into there. So this device is now being programmed. So what I can do is I can actually open a terminal, because I'm still connected, obviously, via the serial port.
But to the right, you can't see the terminal.
Oh, really? Let's see the terminal. Okay.
Don't worry.
So the device has been programmed. It's now it's got a timer on it, which is user programmable, where it just reaches out to the Core Thing and says, "Is there any software for me?" Otherwise, it's just running your product code. So it's having a look for updates. So what you would do is you'd go to firmware, and once you've got a new firmware, if you want to do it manually, you could add the firmware here. So drag and drop it onto the Core Thing. Or you could use our scripting process through your SDLC. You could do it that way, but the idea is you could upload it to here. But I've already got some code up here. I've got some test SE blue and test SE green. You can see it's got a blue LED. So you could upload your software, and then what you do is you go into the device batch and you say, okay, now for all my washing machine batches, I'd like to load my new firmware I've just uploaded, and I'm going to put the green one up because I want the green LED, and I'm going to click save. Now what's happened now is the Core Thing has set a flag so that when all the washing machines happen to call in, how's it going, any software? There's some software. And what's happening now, if I could show the terminal, but what's happening now is this is being updated. I could show the kids at home. %. my phone in. Audio is horrible here. We've got 2 bars, 80%, and that should, fingers crossed, turn green. You know. So basically, you know, this is fully secure. This chip now is bound to this instance of Quantique forever now. I can't change it. It's locked. But hopefully you can see how easy it was to make a fully secure device. Any questions?
I think I'm gonna have to.
Yeah, absolutely. Sorry, I knew I was going to overrun.
But I was keen to show people, this is the book that Chris has asked for as a token of our appreciation. Getting started with ChatGPT and AI chatbots, so I'll be receiving that fairly soon. It's one of the BTS titles. If you're not familiar with BTS titles, try going to bts.org/books. Search all of them.
Quick one. I was at a summit last week, and there was some government people who are dealing with this PQC and security. And the question came up about AI, the question you asked. And he basically said, there's a lot of hype about AI, and it's not as advanced as the media would have us think. There's the notice that went out about that drone that was sent out to try and kill an enemy, and it turned on its operator, came back and actually killed the operator. So that news item went out, right? So this government guy said that is totally and utterly wrong, right? So he did an investigation to find out what actually goes on, where they got that story from. And there are 2 redactions on it. So the first one, they said, oh yeah, the article we sent out, you now put the word killed in inverted commas. He chased it up again, and then they actually got to the general who ran the exercise, and it was initially a thought experiment, and then they ran a simulation. And then it didn't kill the operator. So it was completely wrong. And what I was getting to was, he said, if you want to have a read on actually where AI is, there's a good book called AI Snake Oil. So I actually bought it straight after.
Thank you.
Recommend it.
It's,
Sorry to overrun.